I do need to repeat that, but I'll be quick. Actually, I don't see any indication that this is recording. Okay, there it is. Sorry. All right, so buffers resist change in pH. Acidic buffers maintain acidic pH values, and they're made of acid and conjugate base. And then basic buffers maintain pHs that are in the basic range, and they're made of bases and conjugate acids. So now we need to know what makes up each type of buffer. So we'll start with acidic buffers. So they're going to maintain the acidic range of the pH. And they're going to be made by mixing an aqueous solution. So these do have to be things that can dissolve. And the weak acid is going to be in combination with the salt of its conjugate base. So that sounds really kind of complicated. What that means, the salt of a strong alkali, remember alkali means base. So alkali means base. And salt is not NaCl. Salt refers to anything with an ionic bond. Hopefully that's not new news. So how do we make the salt of the strong alkali? Well, basically, you remove the hydrogen ion, and then you're going to be looking at the conjugate base there. So say, for example, acetic acid, the acetate ion would be the conjugate base, okay? And then that's going to bond with some other cation. So maybe like a sodium acetate or potassium acetate. So we've got the hydrogen removed to form the conjugate base, so that conjugate base is present, but that conjugate base is going to bond with it. And so we want to put those two things in the solution together. So next we're going to look at the actual reaction as an example. So say we have acetic acid, and you notice here C2H3O2 acetate, but bonded with the hydrogen. So we have this carboxylic acid group. And I like to write that out organically. So that's our acetic acid, which we know is a very weak acid. And here's an example of a salt of its strong alkali. So the conjugate base is the acetate, and that's bonded with the sodium. We know that acetic acid is very weak, and therefore its conjugate base would be very strong. Right? That's like an inverse relationship there. So if we put these two things in solution, we're going to get two specific reactions. Each one of them will have their own dissociation reaction. The weak acid, the CH3COOH, weak acid, acetic acid, will have a reversible reaction, forming the acetate ion and dissociating that acid, that proton will come off. But as a weak acid, we know that it's going to have a very poor level of dissociation. Organic acids specifically have almost a negligible dissociation. And so what that really means is the equilibrium is heavily favoring the reverse reaction. There would be much more of a compound in solution, and honestly a negligible amount. As a matter of fact, we're going to talk about assuming there's basically no product later on. So the equilibrium is very, very heavy to the left. So we have this acetic acid absolutely dominant in that equilibrium. That's but mostly physically what's going to be in solution from that dissociation. On the other hand, when you make the salt of the conjugate base here, that dissociation of salt will always dissociate 100%. That ionic bond is like kryptonite. As soon as it hits water, dead in the water. So that ionic bond completely dissociates. You get sodium ions and you get acetate ions. So that means if you put these two things together, like say these solutions are dissociated separately, put them together, that solution is going to be mostly made of acetic acid and acetate ion. And yes, and sodium. We don't really care about sodium. It doesn't matter what salt it's like what metal bonds to the salt. What matters is that we have the weak acid and its conjugate base now in solution, like a lot of it. That's going to make a good buffer for an acidic buffer. All right. So The mixture contains high concentrations of both acetic acid and acetate. We've got this heavily to the left equilibria and complete dissociation for a product. So now the acid and its conjugate base are basically ready to bond. So the acid can neutralize bases and the conjugate base can neutralize acid. The conjugate base being the stronger, right? Weak acid, strong conjugate base. That's going to make it better at buffering for acidic pHs. So what basically happens if we add the acid, now we're just going to look at kind of examples of how the buffering works. So the previous equilibrium stuff was about making the buffer. This part is about the buffer in action. So how does it buffer? And so if we add hydrogen ions, it's going to combine with the conjugate base, which we've talked about as strong, right? And so it's going to remove most of the hydrogen. It'll form acetic acid then. And with that being a weak acid, your equilibrium is going to be mostly to the left. And if we add base, not conjugate, sorry. If we add something that has hydroxide ions with it, acid and base will react. And this basically double, or not double replacement, just the hydrogen then would dissociate and then bond with the hydroxide and form our water. So if we're able to kind of remove the hydrogen or the hydroxide and kind of take that out of solution as ions, then your concentration of those ions in solution doesn't change and the pH doesn't change. So I know this seems a little bit tedious in terms of reactions, but just think about neutralization, right? Acids will neutralize the base, conjugate base will neutralize acid. It's not really something you have to memorize, it kind of makes sense. It's exactly the opposite process for a basic buffer. So we mix a weak base, we want the strong conjugate acid in solution, and we'll get it into solution by having some salt, so some cation to bond. So we want to form the conjugate acid, we would add the hydrogen. That's going to be how we make our conjugate acid, and then it will bond with some other anion. So here's an example of hopefully a really well-known weak base, ammonia. And what it's going to form equilibrium with is going to be ammonium chloride. So this would be a salt of the conjugate acid. So to form the conjugate acid, picture NH3 then bonding with the hydrogen to become NH4 plus. And then it's going to bond with some other anion, positive, negative, so that'll be our salt. Again, you're going to form one equilibrium and one complete dissociation. So the NH3 is going to react with water to form ammonium and hydroxide. And again, since it's weak, it has essentially a negligible dissociation, so very weak forward reaction, very heavy on the reverse reaction. So the equilibrium lies to the left. So you have a lot of ammonium in solution. The ammonium chloride salt is going to break that ionic bond instantly. Complete dissociation, all salts completely dissociate. And so you get ammonium and chloride in solution. So you have your NH3 and you have your NH4 plus. The base and its conjugate acid, very prevalent in the solution because of the way the equilibrium and dissociation work. So just like with the acid, the weak acid or weak base forms an equilibrium that lies heavy to the left, and the salt completely dissociates, and so that's how you get your conjugate in solution. You want both of these things in solution so that you can have your reservoirs again. So the base is capable of neutralizing our acid, and the conjugate acid is capable of neutralizing the base. And again, since the conjugate is the stronger one, the conjugate acid is stronger, it will be better at buffering the bases. So that's why there's the two different types. One's better than one thing than the other. It all depends on the relative strength. Relative strength meaning comparing the acid to its conjugate base or vice versa. Whichever one is stronger is the one that it'll be better at doing the buffering. All right, so then that was how the buffer was made, and this is how the buffer works. So here's our ammonia, the base, capable of neutralizing our acid to form NH4+. And then with our base, we want it to react with the NH4+, the conjugate acid that was actually formed originally. And yeah, we're going to have a little more in solution because of the way neutralizing the acid works, coincidental with in this case. And then you're forming the NH3 in the water, neutralized. So far, so good. Okay. There are a couple naturally existing buffers that you should know about, and you don't need to know the actual mechanism for this, but just know that these things are natural buffers, especially like if you get into environmental stuff with your IAs. Of course, carbon dioxide and water are prevalent in everything. And the ocean has water, of course, carbon dioxide, things, living things, breathing it out. Of course, there's carbon dioxide dissolved in the water to some extent, and it's going to form our carbonic acids. And as you know, from things reacting with carbonate, it likes to break down. It's not going to stay like that. So there is kind of a mechanism of it breaking down, and you have bicarbonate in carbonic acid. So our ocean waters, very highly buffered, which is really good for sea life. And then your blood too, good for us, because there's lots of biological reactions, producing a lot of acids and bases in our body, and we want to make sure that we maintain a consistent pH. So it's important for our cells to survive. So ocean water and blood, highly buffered solution. All right, moving on. So you can actually create a buffer solution that is good for a specific pH. Like say you want to maintain say like we're trying to mimic creating the ocean water pH of 8. So how do I create a buffer that is perfect for that specific pH? So think about the general dissociations that we just wrote. Like I know we wrote specific ones, but think about the general format. We had like acetic acid, for example, this weak acid, the hydrogen with some anion that dissociates into the hydrogen ion and the conjugate base of the anion with that heavy equilibrium to the left. And then we had some metal attached to the anion that would break down into metal and anion, and the weak acid and conjugate base, very heavy in the solution. Okay, that's just kind of general what we just looked at. So there's two things that we can assume, and I've mentioned both of these in passing. The weak acid is so weak that dissociation is negligible. That's why we were able to say the equilibrium lies so far to the left. So what that tells us is obviously we're kind of reading into some math equations here. We're able to make some assumptions, and one of them is that the weak acid has the same initial concentration as it does at equilibrium concentration, which is basically what we did with the small x assumption before when we were doing the icebox. Right, we said the initial concentration basically was the same as equilibrium. The other thing is, since we have a complete dissociation, the salts always 100% dissociate, whatever amount of that initial metal anion was, that's going to be the concentration of whatever the products are. So it's breaking down in a 1-to-1 mole ratio. So we have the same concentration. So that kind of helps us figure out our kind of icebox type of concentration. All right, so we're not actually going to need to set up the icebox. We're just going to make those assumptions. Next, we're going to look at something called the Henderson-Hasselbalch equations. We got pH is equal to pKa plus the log of the ratio of salt to acid, this being the metal anion concentration and our acid concentration, weak acid. And then Basically, same thing with POH, but you use the KB and the bases on the bottom. Pause here for a second, make sure you get those equations copied down perfect. So here's our first math problem. So we're going to calculate the pH of a buffer solution at standard thermal temperature. 298 Kelvin is 25 degrees Celsius. And we're going to mix 25 cubic centimeters or 25 milliliters of 0.1 molarity ethanoate, which is the same as our acetic acid, the CH3COOH, which you should know is our weak acid. We're going to mix it with the same volume of the same concentration of sodium ethanoate, which is basically CH3COO acetate attached to the sodium. So one thing that should be standing out to you right now is we have our acetic acid and we have the conjugate base attached to some other cation. So this is the salt of the strong alkali. So this is a buffered solution. So far, so good. Okay. And then we have the Ka given. So let's think about the assumptions that we're allowed to make. So we have the concentration given of the weak acid, right? That concentration of the weak acid is the same as the concentration at equilibrium. So we're going to be able to use that concentration of the acid right here. Then we're given the concentration of the salt of the strong alkali, but we know that it's going to completely dissociate, so that will be the same concentration as the actual conjugate base. So we're going to be able to use the concentration of the salt, which really is the concentration of the base, which is why we first. So basically, we are given both concentrations that we need here. Any questions before I switch over to about 10 minutes of that? I don't think it's going to work. The doc. I'm going to try to do this with annotations, actually. And I don't have a touch screen, so it's not going to be pretty. All right, so we're going to plug in the concentration of the salt on top. We're going to try to plug in the concentration of the acid on the bottom. And then we're also given the Ka, which is kind of hard to see now. It'll go over on the left. We got pH equals pKa. Actually, we need to find the pKa. I'm sorry, we're given the Ka, but we need to find pKa. Remember, pKa, just like finding pH, we want to find the negative log of the Ka. I'm going to type in negative log 1.8 E negative 5. And because I have two significant figures, I'm going to use two decimal places. So the pKa is 4.74. We'll plug that in here for the pKa. And then plus the log of the salt, oh, they were both 0.1. So obviously the ratio of number to itself, number divided by itself, is just 1. So what is the log of 1? 0. So the pH is actually just a 4.74. So I'm going to clean this up a little bit. if you see, if you, sorry, 1 second. If you see that the concentrations are equal, then a number divided by itself is going to be 1, and the log of 1 is 0. So when the concentrations are equal, the pH is equal to the pKa, and this whole thing zeroes out. Right? Math-wise, that makes sense? That's actually really important. If we know, like when a buffer contains the same concentration, we know that the concentration of the weak acid is the same as the concentration of its the salt of the strong alkali, aka the conjugate base. Then we know that the pH is equal to the pKa. And on the flip side too, we also know the pOH is equal to the pKb. Coming back here. So whenever the concentrations are equal, this whole plus log part goes away, and we know pH equals pKa and pOH equals pKb. Right? So when the moles of acid is the same as the moles of salt, or if the moles of base is the same as the moles of salt, then that whole last term becomes 0. And so those are equal. Kind of exactly what they were trying to show with that math there. And that's the idea. We want that. All right. So this is how we're going to then draw that parallel between pH and pKa, or pOH and pKb. Basically, this tells us the strength of the acid base. So we want to make sure that when we're trying to make a buffer of a specific pH, that we pick out an appropriate acid. So the strength of the acid is typically characterized by its pKa, like literally on the table. Like there's a table in the IB data booklet that has a bunch of acids and what their pKa's are. I believe I have a picture of it down here. There's all these different acids and what all their different pKa's are. So it's important that we try to make sure that this last term zeroes out so that when we pick out the pKa, that is the pH, right? So we're going to specifically kind of mess with the concentration so that we can get, not the concentrations, the volumes, so that we can get the pKa to equal pH, okay? So say, for example, I'm reacting a weak acid with a strong base, like sodium hydroxide. We want to make sure that the concentration of the weak acid is equal to the concentration of the salt of the strong alkali at equilibrium. But the fact that you're reacting it with a strong base is problematic. What happens is the strong acid, we want equilibrium concentration to be equal to the base concentration. So you have to react it with half the volume of the sodium hydroxide. So this is just using like very whole numbers. When you actually work the problems in the book, you'll see like 50 milliliters of the acetic acid to 25 milliliters of the sodium hydroxide. The way this works out is that we're making the sodium hydroxide the limiting reactant because it's the strong base that's going to completely dissociate. So if we do that and we look at the 1-to-1 mole ratio, we would have to have twice as much of the acid to react with the sodium hydroxide in order to get that sodium hydroxide to completely react and get the change to be 1. So we know the sodium hydroxide is going to completely react. So if we have like 1 part sodium hydroxide, minus x equals 0. This is kind of our starting point. We want to make that the limiting reactant with it strong. We're trying to force x to be 1. So that way, that tells us we need twice as much sodium hydroxide, which is going to decrease by 1 to be 1. And we're starting with none of the salt to the strong alkali. So that it increases by 1 to be 1. One more time, because I know this is really weird and tricky. The sodium hydroxide, we want that to be, or that will be the limiting reactant because it's the strong base. So that's the one that's going to have the dissociation. So with that completely dissociating, we want that to be 0. When that's 0, we want to start off with whatever part that is, minus 1 to be 0. So if x is 1, then we know we're not starting with any of the product, so it's going to increase, and so that'll go up to 1, which tells me if I want this to be 1, I need to start with twice the acid. Yeah? Okay. So this is just kind of a sample icebox with whole numbers, just kind of showing you where that comes from. The bottom line of what you need to know, you need twice the weak acid to a strong base. And that's going to get you so that at equilibrium, your weak acid and the conjugate base have the same concentration. And we want that so that pH equals pKa. Okay. That's the part I was most nervous about explaining. All right, so, and we're not going to go through the whole example again with the base, but it would be the same thing. If you have a weak base and you want that to be the buffer solution, you would need twice as much of it with the strong acid. Same idea there, twice as much. So the next thing on your notes is exactly the type of question they like to give you on a test. It seems like a question, but it's actually quite a detailed answer they're looking for. How would you make a buffer solution? And they give you a specific pH that they want the buffer solution to be at. So it's kind of like when in honors, I would ask you, how do you make a solution? And I'm looking for, are you saying the right glassware? Like, do you go into detail about stopping every so often to mix? So they're looking for not just a calculation on a question like this, but also like an explanation. So first of all, we know that since the pH is 3.57, we're going to start off with picking an acid that has a matching pKa. The goal is for the pH to equal the pKa, so then we'll have to get into the volumes and stuff to use. So we want the pKa to be 3.75 because we want a pH of 3.75. Now our job is to make it so that the concentration of the weak acid equals the concentration of its conjugate base at equilibrium. In order for the pH to be equal to the pKa, that's what has to happen for that Henderson-Hasselbalch equation. So one thing is the molarity needs to be the same, equal molar. So that's why you get 0.1 and 0.1. So how do we get that to be the case? We didn't go into words. Okay, so first you find the closest pKa to the pH, and then we want to react the acetic, or it's not acetic acid in this case. What is this? Methanoic acid. So we want to react the methanoic acid with twice the volume of sodium hydroxide. And I guess sodium hydroxide is just kind of an easy go-to, well-known strong acid. Make sure you pick one of the 4 that IB specifically says is strong. So you want twice as much sodium hydroxide as methanoic acid. And I guess they didn't explain that in words on the slides, but that's what they're looking for. Twice as much strong acid, or I'm sorry, strong base as weak acid with equal concentration. All right, so some things that can affect the, I don't want to say strength, but like how well it works, or for how long it will work, how many things, how much it can kind of buffer. And the first one kind of makes sense if you think about it. The dilution isn't going to change the pH because it's not like changing the actual like concentration of ions in the solution. And when they say it does not change the pH, they mean like of the buffer. You know, like we were trying to make a buffer of 3.75. So the dilution doesn't change the pH of the original like buffer solution. But if there's more water in there to particles, there's less particles available to react. So more water kind of in the way. So it won't have as much capacity, meaning you can't put as much acid or base as you could in a concentrated solution. There's less particles there. And then maybe not so intuitive, but if you think about it, Ks have always depended on temperature, even when they were Kc back in honors. So if temperature is changing, it is going to affect the equilibrium. Now the salt was completely dissociating, but the weak acid was, we were saying, just a negligible dissociation. But if you start really significantly changing the temperature, you are going to get more of a polar reaction. And so you can see a little bit of a change in the Ks. Okay, if I was doing the old screencast videos, this is probably where I would cut the video and make this a separate video, kind of a separate topic, kind of changing gears here. So that was all about buffers. Now we're going to get into specifically something called salt hydrolysis. The only real connection between these two, I'm not entirely sure why they're in the same set of notes, but is that it's kind of that salt dissociating that we talked about, like the second step of making the buffer. It is a 100% dissociation. All right, so there are basically 3 types of salt hydrolysis that we need to know about. One is starting with a neutralization reaction. And so we have an acid and a base that form salt and water. And so say you had a strong acid and a strong base, you're going to get that 100% complete dissociation. And you're going to get your anions and forming with the metal, the salt, and the hydrogen and hydroxide forming water, which hopefully you recognize as a reaction, like a neutralization reaction. Okay, so we're going to continue to use these letters though. So M, we're talking about whatever metal was attached to the sodium hydroxide in the first place, or I said sodium hydroxide, so not anything for sodium. And then A for the anion that was originally the acid. Okay. So then, the 2 main types when you do not have a strong acid or strong base. So this is when one of them is weak. You could have anion hydrolysis, which is going to be the conjugate base of the HA, the A minus. So basically, imagine that you have the weak acid that has already produced this anion. The question for hydrolysis is the anion strong enough to break the bond with the water? Almost like a single replacement reaction. Picture this as HOH. Can the A replace one of the H's and bond with the OH instead? Or kick off the OH instead? So the idea is, can it go back to forming the weak acid? And then in this case, it would kick off OH, and so it's going to make a basic solution. So one of the biggest questions when we look at hydrolysis, and this is going to be the big part of the lab, is the pH of the end solution going to be acidic or basic? If the anion is doing the hydrolyzing, how do you say that? Then it's going to be basic. Anion hydrolysis always produces a basic solution. And it is always formed from a weak acid, which then forms a strong conjugate base. It's kind of a chain of events here. You have to have a weak acid that forms a strong conjugate base, and then that strong conjugate base will hydrolyze or split the water. Hydrolysis has to do with the H and the OH breaking up. So if the anion is strong, then it'll break the bond. How do we get a strong base? Or a strong conjugate base? You have a weak original acid. On the flip side, if you have a weak original base, you get a strong conjugate acid. That strong conjugate acid, which is going to be the M, is then going to hydrolyze the water and split it. because it's a cation, it will bond with the OH. And so what you get then is the hydrogen kind of being picked out. And since this time the hydrogen's picked out, you're going to get the acidic pH. So weak base, strong conjugate acid, hydrolyzes water, and you get acidic solution in the end. Cation is the metal. There is a little bit of a complication. Big surprise, transition metals are a pain in the butt. So whenever it's a metal, it does kind of depend on how big the metal is. So they called it charge density here, so how like compacted the charge is, which kind of has to do with size, right? Because density is kind of a function of volume. So the metal ions that are small are going to be better at this because they'll have a higher charge density. So when you get real low on the periodic table, which if you remember is where the real large atoms are, then sometimes they don't have a compact enough charge in order to cause the hydrolysis. All right, so I know this table is a little overwhelming at first. Let's go through it a little bit at a time. Row by row would make the most sense. Strong acid and strong base. So both strong. Strong plus strong, neutral solution. The example here is hydrochloric acid with sodium hydroxide. This would be like the very first example on the bottom of page 13. This is just your simple neutralization, forms NaCl. Nothing is hydrolyzing, and so it's neutral with a pH of 7. Then we have weak acid and strong base. So go to example here with acetic acid and sodium hydroxide. So the acetic acid is then going to form the acetate ion, which will then bond with sodium. So we've got weak acid and salt of strong alkali, which are, would be a buffer too. But the point is that it's going to have anion hydrolysis. So weak acid, strong base, whatever is strong is going to be what the solution ends up as. Remember, with weak acid and strong base, the weak acid has a strong conjugate base. That strong conjugate base. So you get a pH in the basic range. And then on the flip side, strong acid with weak base, there's a couple of examples here. We're going to form the cation hydrolysis because the weak base will have a strong conjugate acid. That strong conjugate acid is going to bond with the OH, and the H will be left in solution, so it's acidic with the lower pHs. So the basic idea between both of these two rows is the strong thing is the type of solution you end up with. Kind of helps you remember it. But the mechanism, you should know the mechanism. It's not because like the strong thing's overriding the weak thing. It's because the weak thing has the strong conjugate that's bonding with the water thing. Like the opposite water thing. And then weak versus weak, we didn't talk about because you can't really generalize it. It depends on which one has the stronger conjugate. So whichever is the weaker is actually going to determine what it ends up as. You would have to compare, here's another key term I've mentioned once or twice, the relative strength. So like compare the conjugate acid and conjugate base, compare their strength and which one everyone is stronger will win. So just because you can't generalize it doesn't mean it doesn't hydrolyze. It just means you can't predict whether it'll be acid or base. It depends on which one's stronger. Well, actually, it depends on which one of these is weaker, because we don't have the stronger conjugate. And that is the end of the notes. So that's it for notes B. The next set of notes is notes E on titration. Go ahead and stop the recording.